Chemical compounds are represented by combinations of chemical symbols called chemical formulas. A chemical formula is going to represent the elements present and the relative numbers of atoms of each element. So in a chemical formula, for example, H2O, it's going to tell you that there's hydrogen present and there's oxygen present, and that there's 2 hydrogen atoms per formula unit and 1 oxygen atom per formula unit. A molecule is a group of bonded atoms that exists as a separate entity and has characteristic physical and chemical properties. Compounds formed from nonmetals are made up of molecules. So the fundamental particles of CCl4 are molecules because carbon and chlorine are both nonmetals. Compounds that are formed between a metal and a nonmetal are made up of ions. So for example, NaCl is made up of ions, and the ratio of sodium ions to chloride ions is 1:1. We're going to use the formula unit to represent these ions. A formula unit is simply made up of the number of bonded atoms or the number of ions in the formula. Now here's where we get into a distinction of terms. When we say 1 mole of sodium chloride, we say there are 6.02 times 10 to the 23rd formula units present. When we say 1 mole of CCl4, we say 6.02 times 10 to the 23rd molecules are present. So it's just kind of a distinction of terms. Formula unit is used when you have a metal. If you just have nonmetals, we're going to say molecules. The empirical formula is the reduced form of a compound. The molecular formula shows the actual number of atoms in each kind of element in the molecule of a compound. So whenever you have the molecular formula, this is the actual formula. So for example, benzene is C6H6. That's what benzene actually is. If I can reduce that, I can get what's known as the empirical formula, the simplest form. The formula mass or formula weight is the sum of the atomic masses in AMUs in the formula unit. So for example, what is the formula mass of MgCl2? If I want to know the formula mass, I'm going to separate it. I got 1 magnesium, so I'm going to take 1 times the mass of an atom of magnesium. Go back to the periodic table. 24.3. And then for chlorine, I have 2 chlorine, so I'm going to take 2 times the formula mass for chlorine, which is 35.5. Gives me 71. And we're simply going to add those together to get the formula mass of MgCl2. So that is 95.3. And the units for formula mass are in atomic mass units because I'm talking about individual atoms. Now the atomic masses of an atom and its ion are practically identical. The ion has lost or gained an electron, and electrons' masses are so small they don't really factor into the formula mass. The molecular mass or molecular weight is the sum of the atomic masses in AMUs in the molecule. It's always acceptable to say formula mass. However, the term molecular mass is only valid if there are discrete molecules. I'm not going to try to trip you up on terminology here, though. Molecular mass, formula mass, we're going to go back to the periodic table and use AMUs. The concept of a mole can be applied to any species, whether they're atoms or ions or molecules. A mole contains 6.02 10 to the 23rd formula units or molecules, and its mass is termed the molar mass. So if I want to know the molar mass of KClO3, I could set it up like this. I've got 1 potassium, so I'd take 1 times the mass of potassium, which is 39.1 from the periodic table. For chlorine, I've got 1 Cl. Its mass is 35.5 from the periodic table. And for oxygen, I have 3 oxygen times the mass is 16.0, and add those together to get the molar mass. Molar mass units are in grams per mole. So that's really the difference between molar mass and formula mass. Formula mass is in AMUs. Molar mass is in grams per mole. Some elements occur in nature as two or more atoms joined together to form molecules. You need to know these diatomic molecules. Hydrogen's kind of by itself, but these elements right here, N through I, they form a number 7 on the periodic table. If you look over there, you'll see NO and then the group 7, F, Cl, and so forth. They form a number 7. And then P4, when it's by itself, phosphorus is P4 and sulfur is S8. So kind of a distinction of terms here. One atom of H means 6.02 times 10 to the 23rd H atoms and has a mass of just 1 gram. But if I say 1 mole of hydrogen, you see the terminology, that means 1 mole of H2, because hydrogen is diatomic when it's by itself, and so it would have a mass of 2 grams. So kind of a distinction of terms. If I say hydrogen, that means H2. If I just want 1 atom of hydrogen, I have to say H. Okay, that's how many H atoms are present in 25.6 grams of sucrose. Let's kind of go through this problem here. We're going to start off with 25.6 grams. We're going to go back to my intermediate unit, which is the mole. In 1 mole of sucrose, to get the number of grams, I would go back to the periodic table and get the molar mass of sucrose. And when you add 12 carbons and 22 hydrogens and 11 oxygens, you get a mass of 342 grams per mole. Now once I get to moles, I'm going to go to H atoms, but I can't go directly from moles to atoms. I first have to go back to molecules because sucrose is composed of molecules. In 1 mole of sucrose, there are 6.02 times 10 to the 23rd molecules of sucrose. From molecules, I can get to atoms of hydrogen. A molecule is this whole entire entity here, but if I'm just looking at the number of hydrogen atoms in a molecule, look at the subscript, there are 22 atoms of hydrogen in 1 molecule. So when I multiply and divide the number of hydrogen atoms, comes out to 9.91 times 10 to the 23rd hydrogen atoms. If I know the chemical formula of a compound, I can get the composition by mass. So what is the percent by mass of each element in aluminum oxide? I want the percent by mass aluminum and oxygen. We'll start with aluminum. If I want the percent by mass aluminum, I'm going to take the mass of aluminum in the compound. Well, the mass of aluminum, I'm just going to take 2 times the molar mass, which is 27. I'm going to divide by the total mass of the compound. So the total mass of this compound from the periodic table, Al2O3, when you add those together, is 102. So the percent by mass aluminum in this compound, which by the way, this percentage will never change for this particular compound. If you have Al2O3, it will always be 52.9% aluminum by mass. Percent oxygen, I'm going to find similarly, we have 3 oxygen, so I'm going to take 3 times the mass of oxygen from the periodic table, which is 16. We're still going to divide by the total mass, which is the 102, and multiply by 100. And that's going to give you the percent by mass oxygen. And 52.9 plus the 47.1, it should add up to 100% because there's only 2 elements in that compound. If I know the percent composition by mass, I can get the empirical formula. I can get the reduced form of the Here's how we're going to do that. A compound consists of 59.9% titanium, 40.1% oxygen by mass. So I'm going to just assume 100 grams. If you assume 100 grams, you have 59.9 grams of titanium. Likewise, if I assume 100 grams, I have 40.1 grams of oxygen. I want to convert those to moles, so get the molar mass of oxygen and titanium. From the periodic table, titanium is 47.9. So we're going to get moles of each one of these elements. Once I get moles, I have to have whole numbers because I want the empirical formula, so I'm going to divide by the smallest number in both cases. Divide both by the smallest number, and hopefully that will give me whole numbers. 2.51 divided by 1.25 is very close to 2 on your calculator. You can go ahead and round that to 2. That's going to tell me the reduced form, so in this case my empirical formula, it may not be the actual formula, but the empirical is TiO2. 1 titanium for every 2 oxygen. Now let's look at a combustion problem. We have a sample of a compound that contains carbon, hydrogen, and oxygen. It's burned in a combustion furnace, and I produce CO2 and water. I want to know the empirical formula of this particular compound. I'm going to get the grams of carbon this way. Carbon is only present in the product CO2. So I'm going to take the mass of CO2 present at the end, which is 0.2998 grams. And I know that for every 44 grams of CO2, there are 12 grams of carbon. 44 is the mass, molar mass of CO2, and 12 is the molar mass of carbon. So this particular ratio, 12 over 44, holds true every single time. So this is going to tell me how much carbon was present in the original substance. 0.08181 grams of carbon originally. I can also get the grams of hydrogen, very similar process, because hydrogen is present only in the water, in the product water. So I'm going to take the 0.0819 grams of water. I'm going to multiply by another ratio. Now the molar mass of water is 18. And out of those 18 grams of water, 2 grams come from hydrogen every single time. So these ratios here are consistent in every combustion problem. When I multiply those and divide, I will get the mass of hydrogen. To get the grams of oxygen, I know that originally I started with 0.2 grams, and since mass can neither be created nor destroyed, I can take my original mass, 0.2, I could subtract the mass of carbon and the mass of hydrogen, and I'll be left with oxygen. Okay, now I've got grams of each element now. And since I have grams of each element, I'm going to go to the next slide, but I can get the empirical formula by starting there with those numbers, converting to moles like I did in the previous problem. So let's start with carbon. I'll take the grams from the previous slide, convert to moles. So carbon is 12 grams per mole. We're going to do the same thing with the hydrogen. Now the molar mass of hydrogen is just 1 gram per mole, so the number does not change. And for oxygen, since there are 3 elements in this compound. Molar mass of oxygen is 16. Now I want the empirical formula. I want whole numbers. So once I get to moles here at the end, I'm going to divide by the smallest number. Well, the smallest number is the 0.006812. So I'm going to divide every single one of these by 0.006812, and hopefully that will give me whole numbers. So the top's 1, the bottom's 1, obviously, but when I divide the 916 by the 6812, you actually get a number that looks like 1.33, which is essentially 1 1/3. I want to get whole numbers. If I have 1 1/3, I'm going to have to multiply by 3 to give me a whole number, which means I multiply all of these by 3. So my empirical formula is going to be 3 carbon. 1.33 times 3 is 4 hydrogen, and then oxygen is also 3. So this is my reduced form, my empirical formula for that combustion reactant. Finally, if I know the empirical formula and the molar mass, I can get the molecular formula. So in this particular example, I know the empirical formula. The reduced form is C3H4O3. I know the molar mass. What is the molecular formula? Well, the first thing I'm going to do is take this compound, and I'm going to get the molar mass of C3H4O3 from the periodic table. So we're going to add those together. 3 carbon, 4 hydrogen, 3 oxygen gives me a mass of 88 atomic mass units. Then I'm going to take the number in the problem, 176. I'm going to divide by the 88. This has to come out to a whole number. In this case, it's 2. So that tells me my molecular formula, the actual formula, is 2 times the empirical. So simply take all those subscripts and multiply by 2 to give me my molecular formula. That's the actual formula for the compound, C6H8O6.